All right, time to do day 3 homework on day 2. Oh, time to get a new pen. There we go. All right. The 2003 blah 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 blah. A particle moves along the x-axis, so that for times greater than or equal to 0, its position is given by this. What time is a particle at rest? So at rest means that the velocity would be 0. So take the derivative of that. And, geez, I expect us to factor that. Well, it would probably help if I knew that. 3 times 2 is 6. It's going to make the factoring a little easier. This is called algebra. So it looks like at 3 and 4, going to be at rest. All right, cool. More no calculator. Maximum acceleration. So if you want to find the maximum of thing, or minimum, then you take the derivative of thing and set it equal to 0. So I actually need to set a prime equal to 0. The classic mistake here is to set acceleration equal to 0. But if you set acceleration equal to 0, then pretty obviously you're not finding the maximum acceleration. You have to find one more derivative. So here's my velocity. So I'll take the derivative of that to find the acceleration. Oops, and then I'm going to take the derivative one more time because I'm trying to find the maximum of this. 3 times 2 is 6. Did you know that? So it looks like at t equals 1. Now I got a closed interval here, so I got to check the endpoints. So I got to check those 3. I'm going to check 1 and then the endpoints. And what am I trying to find the maximum of? The acceleration. So I'm going to plug those into here. So when I plug 0 in, I get 12. When I plug 1 in, I get 3 minus 6 is negative 3 plus 12 is 9. And when I plug 3 in, I get 27 minus 18 is 9 plus 12 is 21. So it turned out that that was a minimum, right? The one that we found by doing our calculus there. And we checked the endpoints. And it was indeed at one of the endpoints. All right. No calculator. Position of a particle moving along a line is given by this. For what values of t is the speed of the particle increasing? So speeding up means that v and a have the same sign. That's what must be true for speeding, and slowing is when they have opposite signs. So here's my position. So I need the velocity. I'm really getting a workout on that 2 times 3 here, huh? I might never forget. 6t squared minus 48t plus 90. And the acceleration, I'll leave a little room for my factoring, my algebra there, is 12t minus 48. So that is equal to 0 at time 4. And this (6 times 8) and 6 times 15 is 90. Minus 5 and minus 3, right? So if I made a sign chart, only interested in things that are bigger than 0. If I put the velocity on the top and the acceleration on the bottom, then it looks like I need 3, 4, and 5. Right? Those are the places where the signs change. This is just a line with a positive slope, so that's going to go negative positive. And this is an upward opening parabola, so that means it's going to be plus, minus, plus. So where is the speed increasing? It looks like it's increasing here from 3 to 4, and here from 5 onward. Okay, look, we got calculator active here. Particle moves along the x-axis so that any time greater than or equal to 0, its velocity is given by this. What's the acceleration of the particle at time 4? If this is I mean, you can take the derivative of that. I know you can. I can too. But this is a calculator active problem, so why would you want to? I'd do it by hand. I'm just going to find the derivative of 3 plus 4.1 cosine 0.9 t at time 4. And just going to check real quick to make sure I'm in radian mode. I am. And 1.63, so that's that. Don't do derivatives and antiderivatives by hand when it's a calculator problem. All right, here, calculator again, particle moves along the x-axis so that for times greater than 0, its acceleration is this. If the velocity of the particle is 2 at time 1, then the velocity of the particle at time the velocity is 2 at time 1, velocity of the particle at time 2 is, okay. So this is a fundamental theorem problem. I have acceleration, I'm trying to get back to velocity. So the integral of velocity from some time to some time is equal to the velocity, because velocity is the antiderivative of that. Right? This is an expression of the fundamental theorem. Now, the times that we're interested in, 1 because I know about that, and 2 because I want to know about that. So I'm going to go from 1 to 2. Right? And I want to know the velocity of the particle at time 2. This is the thing that I'm looking for. Now this I can get out of my calculator by doing math 9. I'm going to go from 1 to 2. The acceleration function, which is the natural log of 1 plus 2 to the x, or the t, whatever. And I could do that separately, but I know what I'm going to end up doing is I'm going to add this over here. So the velocity of the particle is 2. So I'm going to have to add that 2 over to here. And that gives me 3.346. Rounded to 3 College Board decimal places. Two particles, calculator active again, 2 particles start at the origin and move along the x-axis times 0 to 10. Their respective position functions are given by this and this. For how many values do they have the same velocity? Well, same velocity, I guess I'll just, how about if we just graph the velocities of them and see where they intersect on that interval. That'll work, right? So sine t, sorry, this is the position, so the derivative of that is that. You know, I know this is calculator active. That's just too easy to take the derivative of that. So v2 would be negative 2e to the negative 2t, and then that goes away when you take the derivative. So I guess I'm eating my own words here. Use your best judgment. That, right? And then the window, excuse me, from 0 to 10. And we'll see how that works out, if we can see everything or not. Oh yeah, we'll be fine. Ooh, they're kind of close. What the? Oh, I guess that just became asymptotic to that. Just to be sure here, I'm going to do a couple of things here. First of all, I would like to see like zoomed in more, so let's go from like -2 to 2 instead of 10 to 10. Okay, so this is asymptotic to this axis. If you're like, oh, only intersects one time, then you're not really looking at, I mean, this graph doesn't like stop existing. So I'm just going to show you one other trick that comes in handy sometimes. I think we could be pretty confident saying here that it intersects 1, 2, there's 3 of them. But if you felt a little hesitant because you can't see that graph, I want to show you that you can go to a Format, Second, Zoom right here, and you can turn the axes off. So if there's some graph, if for whatever reason the axes are getting in the way of what you want to see, you can turn them off, and then we can see 1, 2, 3. There they are. Okay, got another calculator problem here. Particle travels along a straight line with this velocity. What's the total distance traveled by the particle during the time from 0 to 2? So total distance traveled, remember that that is the integral of speed. Oops, I was saying speed and trying to write a 2 at the same time. My brain doesn't handle that very well. So 0 to 2 of the speed, in other words, the absolute value of the velocity. And it's a calculator problem. So you can either do this, you could put that into your y equals and then do it that way, or you can just do it all on the home screen like this. Math 9, the integral from 0 to 2 of the absolute value of this 3e to the minus t over 2 times, you put a little time sign there, but calculator knows that that means multiply, 2d. I think that's good. And then just have to put my dx. Oh, it looks like I might need a close parentheses there. That's better. Calculator might have been okay with that, syntax-wise. Come on, buddy. 2.261. Oops. All right. I got a calculator free response question. Particle moves along the y-axis so that the velocity at time greater than 0 is this. And at time 0, the particle is at this. I mean, that should make you think, oh, there's going to be some fundamental theorem coming up here. You'd be right to think that. Find the acceleration at time 2. I'm going to go ahead, because this is a free response question and I'm expecting to have to do a bunch of stuff with this, I'm going to put my velocity function 1 minus tangent inverse of e to the t. Put it in here. Is it e to the t or e to the negative t? T. All right, so I'm going to put that in my y1. And then for times greater than 0, so if you wanted to see what it looks like, my window right now is 0 to 10, so that probably is fine. I don't know about those. Oh, my axes are still off. Oops. Let's turn this back on. That turned out to be a pretty good window for it. Okay. Find the acceleration of the particle at time 2. Well, the acceleration of the particle at time 2 So dv dt at time equals 2. I'm just writing this down just in case. I mean, this is most likely a one-pointer for this part, like just having the right answer. I'm going to write that it's the dv dt at time 2, just in case there's some like point for knowing that acceleration is the derivative of velocity. So since I have this on screen here, I can do second calculate dy dx at time 2. It's negative 0.133. Is the speed of the particle increasing or decreasing at time 2? Well, acceleration is negative. Just found it. And the velocity, I just need to find the value. So second calculate, number 1, the value at x equals 2 is also negative. So the speed is increasing because they have the same sign. Find the time greater than or equal to 0 at which the particle reaches its highest point. Justify your answer. Okay. Well, position is max when velocity goes from positive to negative, and this happens, or endpoint, right? And there is an endpoint at 0. Probably one point attached to recognizing, like making somewhere in your explanation that you can't just check where the velocity is 0. You do have to be sure that it's not somewhere else like an endpoint. Or the endpoint is at t0, and we have that. We don't have to do any work to get that. Time 0, the particle's at negative 1. So I need to find that. That happens at where that's equal to 0. Left bound and right bound, I don't like playing this cursor game. I'm just going to type in. It's in between 0 and 1. So 0, left bound, 1, right bound. So that's at 0.443. And this is the only 0. Only 0 of ut. So this is the absolute max. Right? Because it doesn't happen, it's increasing from 0, so it can't be at that endpoint. Find the position of the particle at time 2. Is the particle moving toward the origin or away from the origin? Find the position at time 2. I have the velocity, so I want to get back to position. This is the Fundo theorem of calculus. So I know time 0, and I want to know time 2. So that's the position at time 2 minus the position at time 0. Certainly points attached. Probably this is 3 points. That would be one of the points, and using the initial condition here would probably be another point. And, oh, man, this could be a 4-pointer. This could be like 1, 2, 2, 4 maybe, because of this other part of the question. Find the position of the particle. So here, I'm going to do the integral here. I can do it here in the home on the graph screen rather from my calculate menu. Lower limit 0, upper limit 2, and it shades it in, which I never stop thinking that is cool. negative 0.361 is equal to x of 2 minus the position at time 0 is negative 1. So I need to subtract 1. So the position at time 2 is equal to negative 1.361 after I subtract 1 to the other side. So is it moving toward the origin or away from the origin? Well, it's on the left side of the origin because it's in negative territory, and its velocity at time 2 is negative. So it's on the negative side, moving in the negative direction. So it's moving away from the origin. And we can justify in exactly that way because the position is negative, and so is the velocity. That's a little crowded there. I probably shouldn't have done that all in that little tiny space, but oh well. Okay. No calculator here. Rocket A has velocities here after being launched upward from an initial height of 0 at time 0. The velocity of the rocket is recorded for selected values from 0 to 80. Find the average acceleration of the rocket over this time interval. So average acceleration, that's like just old school slope. Acceleration is the slope of velocity, and if we're looking for average, then it's just really the slope. So the velocity at 80 minus the velocity at 0 over 80, and that would be feet per second per second. All right. Using the correct units, explain the meaning of this in terms of the rocket's flight. The area under velocity is displacement. So displacement on the time interval from 10 to 70. Use a midpoint Riemann sum with 3 subintervals of equal length to approximate this. So from 10 to 70, if we wanted 3 subintervals of equal length, that would be those. So a midpoint Riemann sums are rectangles, remember. So this rectangle is 20 wide, and then I'm going to use the middle value for the height of it, because they told me to do a midpoint sum. And then this rectangle is 20 wide and 35 high. And this rectangle here is 20 wide and 44 high. Now, believe it or not, you can just leave your answer like that if you want to. This is a no calculator problem, so if you want to try to do something more with this, you got to do it by hand. So let's see, 22 plus 35 is 57, 101 times 2 is 202. Right, and that would be feet. All right. Rocket B is launched upward with an acceleration of this feet per second at time 0. The initial height of the rocket is 0 feet, and the initial velocity is 2 feet per second. So it smells like more fundamental theorem. Which of the two rockets is traveling faster at time 80? Well, I know that at time 80 this one's going 49, so I just need to find how fast is this one going. I've got its acceleration, and I want to get back to velocity. So the integral of acceleration gives me velocity, but it gives me change in velocity, right? So I'm going to go from 0 to 80. For this, this is a no calculator problem, so I've got to do this by hand. Do it down in this little corner here. So let's see, I need to do the integral from 0 to 80 of 3 times t plus 1 to the negative 1/2 dt. I'm going to do a u substitution here, just to make things a little bit easier. So du is just equal to dt. It's just a straight swap, but it's going to let me get nice numbers here, and it might, I think it's going to clean it up just a little bit. So it turns this integral into now t plus 1, 1 and 81. That's good news. Those are both perfect squares. I'm going to move the 3 to the outside. I did not need to make an adjustment there for my u substitution. And then I have u to the negative 1/2. Antiderivative u to the negative 1/2 is bump the exponent up 1 and divide by the new exponents. It's 2u to the 1/2. That's going to be 9 minus 1. That's 48. And there we go. So rocket A is faster at time 80. And if you're thinking, well, what about our explanation? This is the explanation. So I just need to make sure that we know this is the speed of rocket B at time 80. That's what we found here. Oh, wait a minute. Oh my goodness. I'm so glad I caught that. And weren't they cute in making it so close? I forgot this. Right? I have to add the initial condition, 2 feet per second. So that is just enough to push it over the edge. Rocket B is faster at time 80 because its velocity is 50. And velocity of this one from the table is just 49. So there you have it, folks.